I will take the silence to mean there are no questions. In that case, I will move quickly on to the pitch talk session of today. Just ask that all those presenting are ready with their slides. I'll just quickly share some slides myself as well, just to set some rules for presenting.
You start the intro. Yeah, have the class on. See that you when I'm presenting. Yeah.
Hopefully.
It's good.
So, just to highlight that during the pitch talk session, we'll invite those who've been invited to speak to present their 2-minute pitch talk slides. Please keep to 2 minutes time only to allow sufficient time for all presenters to speak. And please have your slides or video ready to present. We have put in the chat the order of presenters, but if you need reminding, please let us know. And for all those in attendees, please save any questions until the group discussions, or alternatively, please use the Zoom chat, or if there isn't time to do so, please pose your questions directly to the relevant individual directly after the workshop. I will stop sharing my screen and then allow people who are presenting to start presenting themselves. So we have the first presenter up, which is Adam Green from the University of West of England.
Yeah, I'm here. Thank you, Adam. So I'm going to start sharing my screen. Can you see my screen?
Yes, but it's not in presenter mode.
Yeah, so I'm going to present that. So that's in the...
You're in presenter mode, but with the text on the side.
Okay, so we can switch. Okay, so I'm going to come out of the sharing and share the other one. So
if you click display settings at the top left of your screen where it says display settings,
top left display.
the middle icon with the drop down triangle. Yep, that one there, perfect. And then click the swap presenter view and slideshow, and that should be good.
Better?
Perfect, thank you.
Got that, okay, great, thank you. Right, so we're going to move slightly to a different application. We're going to explore AES, which is Advanced Encryption System Vulnerability with Quantum Technology. So my name is Adam Green, and my research associate, Mohammed Suhaib. We are from the University of the West of England, Bristol, UK. And we are a team of researchers dedicated to advancing the field of cybersecurity, cryptography, and quantum computing. And today, we aim to share insights from our research, which bridges these areas. So we're going to look at the expertise in quantum computing and research collaboration and conclusion. So this presentation, the purpose for this presentation is we use Grover's algorithm, which is a powerful quantum computing tool to analyze the vulnerability of AES. So AES is based on a key, which is the it's like a password, which could be 128, 256. So we're trying to break that key, basically using quantum computing. So as quantum computing technology mature, classical cryptographic systems like AES face potential threats. Exploring and understanding these risks is crucial to preparing for quantum secure future. So what are our expertise in this area? We've already implemented Grover's algorithm to analyze AES vulnerability. We used quantum error correction to tackle hardware noise, and even demonstrated the vulnerability of a simplified. So we took a simplified version of AES. So AES, as I said, it could be 128-bit. We took only 4 bits AES, and using the resource we have at the moment, IBM quantum hardware, we managed to break that 4 bits, showing case Grover's algorithm quadratic speed. So Grover's algorithm allow you to, instead of searching the whole space of 128, you could search only break it, so bring it to 64, which is quite an achievement. So our research has been recognized through a publication in the American Journal of Computer Science. So recently we've applied. If you're interested, you could have a look at that. Collaboration. So what we want to do, the next research bit, we want to analyze 128 bits and even 256-bit AES vulnerability using advanced quantum processing unit. And we want to scale that. So we want to scale quantum cryptographic attack to address practical cryptographic challenges. We want also to enhance the quantum error correction technique to reduce noise and improve accuracy. In conclusion, so we're looking for a partner. Let's redefine. So our goal is to seek in collaboration with researchers in the UK and Japan to advance our work in quantum cryptography. Our goal includes analyzing the vulnerability of 128-bit and 256 AES encryption using cutting-edge quantum processing unit, scaling quantum cryptographic attacks to address real-world challenges, and enhance quantum. So additionally, we're also looking for funding opportunity to support our expanding this critical research area. Thank you.
Thank you, Adam. For the sake of time, I will invite the next speaker. So it's Edmund from the University of Bristol.
Oh, hello, Adam. I've just sent you a sharing request.
Okay.
Okay, who's that?
It could be that you can't share because someone was already sharing.
Let's try that one again. Let's try that one again.
Okay.
Excellent. Can you see and hear me? Fantastic. Good morning, everyone in the UK, and good evening to everyone in Japan. My name is Edmund Harwood. I'm a senior lecturer in quantum communications technologies at the University of Bristol. And I'm interested in collaborating to build devices for the future quantum internet. My area of expertise and research focuses on quantum emitters made of semiconductors, single quantum dots, and using them as sources of light for quantum communications, but also as spin-photon interfaces, two technologies that are key to quantum networks. Some recent work that we've done here at Bristol is shown here, using semiconductor micropillars to very, very efficiently generate single photon sources and to encourage interaction between bandwidth mismatched photons and quantum dots. In terms of spin interface work, we're able to use a single spin in a quantum dot as a memory and monitor its manipulation. And more, most recent work has been in developing developing designs to exploit TAM states, a very easy to manufacture technology that efficiently funnels photons into an optical mode. And that's the focus of my new investigator award, which I received from EPSA. So that's my expertise. What I want to collaborate on is heterogeneous integration on photonic integrated circuits. So one of the major challenges of these highly efficient single photon sources is they are made from 3.5 semiconductors, from gallium arsenide and indium arsenide. But if we actually want to achieve a scalable quantum communications technology, we need to pack those onto a photonic integrated circuit. And Japan has a lot of expertise in heterogeneous integration between different materials, and I'd like to collaborate and work with people on developing that. So just to review, because I'm coming up to my my time now, I work on semiconductor quantum emitters, spin photon interfaces. I want to collaborate on heterogeneous integration on photonic integrated circuits, and you're very welcome to contact me on my email address, edmund.harboard@bristol.ac.uk. And I believe we're going to share everybody's contact details who opts in. Is that right, Adam? Fantastic. Brilliant. Thank you very much.
Thank you. I'm now going to invite the next speaker. So we have Ashley Delavar from the University of Sheffield. Thank you.
Hello. So just let me share my screen. Can you see my screen now? Hello?
Not yet. We can now. Yeah.
No? Okay. So hello everyone. So it's an honor to be here at this networking fair. Thanks for organizing this fantastic event. My name is Mashoud Delaban. I'm a lecturer in the School of Computer Science at the University of Sheffield. So, you know that we are living in the area of rapidly emerging technologies, and first, you know, the internet revolutionized the telecommunication industry. Then we moved into the world of connected devices, which is the Internet of Things, and now we are heading towards a fully connected world with several critical infrastructure. And beyond this, with the advancements in quantum technology and research pushing the boundaries of quantum internet, the future kind of is clear. The networks will evolve into hybrid quantum classical systems, as also envisioned in the quantum network white paper published by National Institute of Information and Communication Technologies in Japan. So while these advancements promise you know, countless benefits, enhancing everyday lives and improving quality of life, they also introduce significant security concerns. And without effective solutions, these vulnerabilities can lead to financial losses, disruption to essential services like electricity, and in severe cases, threats to human lives. Over the last decade, my research has focused on advancing cybersecurity and privacy through innovative solutions addressing emerging threats in communication systems, the Internet of Things, and also the quantum communication. Building on this foundation, my current research lies at the intersection of quantum technology and cybersecurity, which is the first one is I aim to enhance the security of tamper-proof hardware. And also, I want to redefine security concepts in the presence of quantum adversaries, which are very powerful adversaries. And finally, I want to develop lightweight post-quantum authentication and key management protocols for secure communication in messaging protocols like WhatsApp and Signal and whatever. So browsing through the security fundamentals laboratory, I found my research interests perfectly aligned with their work on the security evaluation of cryptographic technologies. And I hope to connect with researchers from this lab or other Japanese institutes like QIQB, that after the talk I found that we have also research, I have research, you know, common research interest with this QIQB too. And I'm happy to collaborate with Japanese, with you know, brilliant researchers from Japan. And this is my contact information, and Delavar at sheffield.ac.uk. And thank you for your time.
Thank you. I'll now invite the next speaker. So we have Nobuku Yoshida from the University of Oxford. If you could put your slides up, please. We can see your slides, but we can't hear you at the moment if you're talking.
Sorry, my name is Nobuko Yoshida from Department of Computer Science, University of Oxford. Actually, I took the PhD at the University of Keio and also joint degree with University of Manchester. And my starting point is actually electronic engineering. So I'm quite familiar with more like quantum mechanics side. And then after that, I moved to Edinburgh and Sussex, Leicester and Imperial for a while. And then recently moved to Oxford, taking the Christopher Storage Chair of Computing. And one of the reasons why I took the, I moved to the Oxford is that I want to really start with learning quantum computing, and together with my very active colleagues. There are several names and institutions already mentioned in the previous communications. So my expert is modeling communication concurrent and distributed computational models and materialized to the programming language and system. In particular, I'm also interested in verifications. And my area of concurrent process and quantum computing is a very now quantum extension of concurrent process model called CCS and PyCalculus, and these things are very active area now. The reason is that quantum computing, you can, using concurrent process model, you can reason about what is the actually equivalent, so that you can use this theory to optimize the circuit or optimize the protocol, or even you can verify the correctness of the protocols. And also, quantum communication protocol mentioned by the first pitch talk is that, for example, cryptographic protocols such as teleportation, secret sharing, bit commitment, and key distribution, these things can be verified by theory of concurrent processes. And so I'm going to the next slide. So what I'm interested in that I want to use type theory and actually protocol verifications to specify and verify the quantum, for example, cryptography protocols using the called session types, multi-party session types, and which is used to ensure the linearity of the channel so that non-cloning theorem can be verified statically very easily and give the guidance to the user to be able to write protocol more friendly. For example, currently quantum protocols use there a lot of libraries and a lot of specifications of the protocol, but these things are very difficult to written down. And I'm very interested in ensuring correctness, for example, using the probabilistic model checking, such as deadlock freedom and liveness, and quantum non-growing and non-deleting theorems. So I'm part of, probably Mohammed will talk about our project more, but more side of I'm interested in the verification, programming, and software, and want to talk about many people in the Japan who are interested in, for example, to bridge the user side of the usabilities, and also verify the correctness of the protocols. And also I want to bring the very active activity of the Oxford, and as already mentioned in the talk, previous talk. Thank you very much.
Thank you. Can I invite the next, in fact, we don't need to invite a next speaker because we're going to put a video up. Bear with us a second.
So the next speaker has sent a video, so I'm just going to play that from my screen. Okay.
Hello everyone. The University of Southampton has excellent clean room facility for the semiconductor nanofabrication, and my expertise include silicon quantum devices, names and noise, and heterogeneous materials integration. In near term, I want to use my expertise on names and noise for the quantum technology applications that include the development of the optical switches for the quantum state control, the integration of metamaterials for the functionality, and development of the entangled pair photon source via material integration. Those are not only for the quantum computing, but also the quantum communication, quantum sensors, and quantum biology study. In longer term, I want to develop these nanochemical qubits, which are known to have a longer coherence time with high quality factor. Qubits can be realized with strong unharmonicity, which are reported recently, and I'm really interested in developing this new qubit platform by using my fabrication expertise. I'm Yoshitsu Chiura, Associate Professor at the School of Electronics and Computer Science. I'm a UK-based Japanese researcher having work experience in both countries. I have also the experience of UK-Japan and international collaboration. I'm also co-I of the Quantum Technology Engineering CET, which can provide joint PhD students application opportunity for our collaboration. I really look forward to discussing the potential collaboration with you. Thank you very much for your kind attention.
Thank you.
Okay, so thank you very much for giving me the opportunity to present today. I'm Shuta Kikuchi, a project assistant professor at Keio University. And today, I will be presenting on the topic enhancing the performance of quantum annealing machines. The quantum annealing machine, which I will refer to as QA machines, are expected to the efficient solvers for combinatorial optimization problems. However, their performance is limited due to hardware restrictions. Example of these restrictions including topology and spin size and coefficient range and the binary variables. My research aims to mitigate these hardware restrictions, enhance the performance of QA machines, and move toward real-world applications. Let me discuss the spin size restrictions, which refer to the limitation on the size of programs that can be input into QA machines. For example, the D-Wave advantage, which is most widely used, can handle up to 5,000 variables. However, this is still insufficient for solving realistic problems. To address this spin size restriction, we proposed variable reduction methods that combine the classical solver with a QA machine. First, the classical solver generates multiple candidate solutions. Then, by fixing the persistent variables among these solutions, the problem size is reduced. And finally, the reduced problem is solving using the QA machine. This method has demonstrated better performance compared to using the D-Wave advantage or a classical solver alone. And in addition to this, we have proposed the algorithm to mitigate the coefficient range restriction and conduct research on effective transformation technique for representing integers by binary variables. So I hope to collaborate on further development these methods or exploring other approach to mitigate hardware restrictions. Thank you for your attention.
Thank you. Can I invite our next speaker to put slides up? Just to remind everyone, please stick to 2 minutes because I'm conscious of time.
Hello, everyone. I'm Paul Warburton. I'm Professor of Nanoelectronics at University College London, here in the centre of London. I'm an experimentalist and I work on quantum annealing with superconducting qubits. Move on to the next page. So I guess these are the overall goals of the research in my group. I want to look at the limitations of the current implementations of quantum annealing on, for example, the D-Wave device, which Kikuchi-san was speaking about in the previous presentation. So we interact with the D-Wave device, we interact with the Quira-Rydberg device as well. Excuse me. We want to think about what functionality we could add to future quantum annealers, which might enable us to overcome these limitations. And then finally, since I'm an experimentalist, here's the fundamental question is, how do we engineer devices that allow us to implement that functionality, which might allow us to, for example, see a quantum speed up in quantum annealing? So as a couple of examples of the work that in my group we've undertaken, here's some collaborative work with my colleague Sagato Bose, also at UCL. You can see the citations on the left if you want to learn more about this. So here in simulation work, we're plotting the energy gap as a function of the annealing parameter. Notice the logarithmic scale on the energy gap. And one of the bottlenecks in quantum annealing is this point in blue down here, where you have a very small energy gap between the ground state and the first excited state, which means you have to anneal very slowly. And what we've done, so the blue points are with a conventional X driver, such as you find on the D-Wave machine. If you add new, qualitatively new interactions like an XX catalyst, or even better, an XXX catalyst, you can enhance this minimum gap by orders of magnitude, enabling you to potentially address a quantum speed up. So that's theoretical and numerical work in my group. In terms of the experimental work, we have a nice clean room here at UCL in the London Centre for Nanotechnology that we use regularly. What I'm talking about here is using our electron beam lithography and our sputtering facilities, for example, to make these superconducting nanowires. These could offer some nonlinear capacitance, which would allow us to implement, for example, a Y-Y interaction between superconducting flux qubits. And so I have a program of work looking at how to exploit this nonlinear capacitance using these coherent quantum phase slips in superconducting nanowires. That's all I have to say. I look forward to establishing collaborations with partners in the UK and Japan. So please send me an email if you're interested. Thank you very much.
Thank you, Paul. Can I invite the next speaker to put the slides up, please?
Okay, thank you very much for the organization, and then thank you very much for this opportunity. I'm Hiroki Takahashi, and let me just introduce myself here and my group. I'm currently a PI of a research unit at Okinawa Institute of Science and Technology, which is a young graduate university in Okinawa, Japan. And I'm leading a team of 4 postdocs, 5 PhD students, and 3 technicians, 1 administrator. As a group, as a research group, we specialize in ion traps and the cavity QED experiments. And talking about myself more, previously I was a postdoc at the University of Sussex, and I worked with Wolfgang Lange and then Matthias Keller, and then spent some time on the South Coast. And one of the achievements we made there was this one, the strong coupling of the trapped ion in cavity QED. And then, as you can see, we are kind of continuing the work in Okinawa as well. So in the next slide, so this is what we are doing right now. So as you can see, this, sorry, let me show you a pointer. So this is a model of a device, of the device that we are building right now. It has an ion trap as well as a fiber-based optical microcavity in the trap. And then we want to combine the cavity and the ion trap. And then we want to make an efficient interface between the ions and photons. And eventually we want to create a network of ion traps, something like this, with the traveling photons connecting ions. And so that's our goal at the moment. And talking about more technical size of our research, we established a way to fabricate ion traps using a technique called selective laser etching. It's a kind of 3D printing of glass. So here we make a substrate of the trap, and then we put gold coating on that, and then that makes an ion trap like that. And also we have a means to fabricate the mirror substrate on the end facets of an optical fiber like this. We use the CO2 laser ablation for that. And we are also interested in other photonic and integration technologies such as MEMS actuated cavities and waveguides, and then the modulation in waveguides, and of course lasers and electronics and so on are at the heart of our interests. And then I'm looking forward to any collaboration in any of those and beyond. Thank you very much for your attention.
Thank you. Can I ask the next speaker to put the slides up when ready?
Thank you very much. Could you please confirm whether you can see the slides?
Yes, we can see them. Thank you.
Thank you very much. I hope the noise is not too much disturbing. I have to teach very soon, so I stepped out of the teaching theater and I'll have to go back in about half an hour. My name is Mohammed Musavi. I'm the co-director of King's Quantum. Like many other centers that were presented before, this is a young center at King's College London. And the website is advertised here. Please visit the website. There are lots of activities ongoing across many different disciplines, but in quantum technology. But the discipline I'm representing is quantum software engineering, and I'll mostly focus on that during my presentation. Before going a bit deeper into my area of research, the vision of King's Quantum is to bring quantum technology to early adopters of such technologies. And you may know King's College London has one of the largest medical schools in the UK. And one of our main target applications are healthcare applications and medical applications, ranging from sensing to imaging to quantum computing. So we have a lot of activities organized jointly with biologists, chemists, physicists, and in particular, medical experts to see how we could bring quantum technology to actual application. That's our vision, and that's what we are striving for at King's Quantum. Now, more specifically about my personal interest and my personal research, thanks to Nobuko Yoshida for the nudge to our joint research. We have funding from EPSRC on software-enabled quantum. We have had funding from STFC on commercialization of quantum software engineering. And also we are running one of the projects mentioned by NQCC with BT on the secure line in London together with British Telecom and Toshiba and other companies, looking at quality assurance of the software that is running on that secure line. Our vision is to develop compositional and expressive methods for different types of quantum systems, ranging from NISQ architectures, currently noisy architectures, to future fault-tolerant ones, to adiabatic computing that was presented in the previous slide, having one type of uniform specification framework for the different types of systems, and also making sure that they can be translated in a verifiable manner to actual architectures. We have developed some extensive testing and quality assurance libraries for quantum computing, and we are looking at extending that to distributed and concurrent quantum computing platforms together with people at Oxford and other institutions. We are currently working with people at Condensed Matter Physics on applying that to modeling fermionic systems, but we are also exploring other applications in biological systems and also in medical applications. That's our ongoing effort. I'll stop here given the time, and I will put in my email address, and I'm very much looking forward to collaborating with people in the audience. Thank you very much.
Thank you. Can I ask the next speaker to put their slides up, please?
So I may need to swap the views. Can you see the correct view?
If you just swap it over now, and then we'll
Just
have
swap it
the Perfect, thank you.
There we go. Great. Well, thank you very much for the invitation to talk to you all today. Looking forward to some fruitful discussions in the future. So I'm Mark Basin. I come from RAL Space. So for some of you who may not have heard of us, we're the UK's National Laboratory for Space. So we do everything from the science to the engineering to the testing. So here's a few images from our new facility, the National Satellite Test Facility. So to qualify the satellites we put in space, we put them through these types of thermal vacuum testing. We have shaking, we have shock testing. We do it all. So in terms of quantum technologies, we have current projects that are around acceleration, magnetic field measurements, radio frequencies using Rydberg sensors, and quantum communications. So we also have ambitions to do future sensors such as clocks, which are sensors of time, rotations, and then quantum memories. So looking at the first of these, acceleration, so we have quite a lot of activity in atom interferometry. So the applications of these are many and varied. So for example, we want to look at the effect of the sun on the Earth's atmosphere. So looking at atmospheric drag using accelerometers. We're also interested in fundamental physics. So we're part of a ground-based project, which is called AEON, which is looking at using strontium atom interferometry for gravitational wave detection and searching for ultralight dark matter. We've developed custom electronics for space, 3D printed vacuum chambers and atom chip capabilities. And so we're looking to expand upon these in the future. A second part of what we do is in quantum communications. So this work is led by Andy Vick here. So there's 2 missions launching next year called Spectre and Spock, which are done in collaboration with various friends across the UK and in Singapore. So we're responsible for the classical aspect of this, so that the quantum payload is given by someone else. And so our team is meeting the challenge of being able to do the classical optics and qualification for this. Then lastly, we're interested in magnetic field measurements and Rydberg sensing. So the applications of the magnetic field measurements are in space weather. So again, looking at the effects of the sun on the Earth, and then collecting data, which is used, magnetic data, which is used in navigation. Then we've recently got into the use of Rydberg sensing. And so there's aspects of Earth observation, which may have an advantage from using Rydberg sensors, and then radar. Okay, that's a very quick run through of our capabilities. If you have any points of interest there, please do get in contact with me, and I'm happy to take any questions later. Thank you.
Thank you. Can I ask the next presenter to put their slides up, please? Thank you.
So hopefully you can see my desktop.
And now, yeah.
Great. So good morning, konbanwa. I just want to talk about a proposal for a new quantum tech-based dark matter experiment that we call QUADMOS. So this is at a conceptual phase, but we're building an international collaboration of people trying to look at using quantum sensors to search for light dark matter. You'll hear from some of my colleagues, including Yan Mol and Junji Liu shortly. And the idea here is that we're interested in quantum sensor interaction with different types of radiation in order to understand our background, as well as the implications of that in the context of searching for ultralight dark matter that would be generating athermal photons in a sapphire crystal. We've got some industry interactions, and we work with people at the STFC, particularly the Bulby Laboratory, which is based 1.1 kilometers underground in North Yorkshire. And there's a complementary laboratory, Snow Lab, which is 2.1 kilometers underground in Canada. So we want to develop sensing technologies based on kinetic induction detectors and Coulomb blockade thermometers to search for dark matter. The conceptual design has a 16 by 16 grid array on a 6-inch wafer, and we want to be able to scale up from individual devices that we're working on at the moment to a concept where we would have about a stack of about 8 of these wafers, so 1.2 kilograms. That presents a whole host of challenges in terms of making sure that we go from making single devices to something that's a little bit more production ready. That's one of the reasons why we're looking to partner with companies there, and also then multiplexing those signals out and trying to deal with the data processing for this. And the reason why we want to do this is because if you think about the universe around us, about 75% of this stuff is dark energy. There's about 5% that's the baryonic matter, so the stuff around us. And then 23% of the universe, or the energy in the universe, is dark matter, and we have no real idea of what that is. And so this is really the quantum technology aspect, building the devices, trying to be able to read them out, trying to be able to characterize them, understand their interactions with matter. Now, there are parallels there. Understanding radiation interaction with quantum sensors will feed into our ability to understand the ability to do quantum computing calculations, because these radiation interactions with our devices that we would consider to be signals would be things that would be affecting quantum computation algorithms and causing decorrelation effects and decoherence of wave function for your computation. Now we've got a conceptual design that is shown here, and the idea is that we squirrel this system away. So we have a Dill fridge surrounded by a neutron field deep underground. So we go about a factor of 1 million down on the cosmic microwave background radiation. That's the radiation environment that we live with, the surface of the Earth. And that now with these designs, we're working towards starting to sensor testing. And we're just targeting, if you look at the graphic on the right-hand side, those very, very light dark matter energy scales just indicated over here. And you can see that there are several different technology sites, and we're sort of sitting in this regime here on this little line there. I'll pop my email in the chat if you want to reach out. Really open to collaboration. Would be absolutely wonderful to be able to work on something following on from this meeting. Thank you.
Thank you. Can I ask the next speaker to put the slide to please?
Yep. Yeah, hello. Can you hear me? Yeah. Hello. I'm Masatsumi Fujiwara from Okayama University, Japan, and I'm talking about nano-diamond quantum thermometer. So, let me. Yeah, this is a brief introduction of a group, and we are in Okayama. Okayama is actually around here, and it's actually 150 kilometers west from Osaka areas in Japan. This is our team. We have several the international students, and also we are collaborating with some other countries, Germany and also the US. But I recently started talking about collaboration with some teams in the UK. So I'm happy to collaborate with other partners in the UK. And Okayama is known to be known to be by very beautiful Japanese gardens or some modern island of modern museums. So if you come to Japan, so please visit us. And we are working on diamond quantum sensing. So this is diamond structures, and particularly we are working on nitrogen impurities incorporated in diamonds. And if the adjacent site of the nitrogen is a vacancy, then they are working as a the defect center called nitrogen vacancy NV centers, and it actually has electron spin activities. So and also it can be read out by the fluorescence. So this is the fluorescence, the fluorescence intensities, and you are sweeping the microwave frequency, which is resonant to the electron spins. Then you get this kind of the electron spin resonance by optical means. And if you apply the magnetic field, this the spin resonance is splitted by the Zeeman splitting, so you can read the magnetic field around these diamonds or NV centers, and then you can use, for example, the visualization of magnetic fields, and also people are working on single molecule NMRs. I'm working on the temperature measurement by detecting the shift of this resonance peaks. And for example, the previously we worked on feeding these diamonds into the small diamond particles into the worms, then measure the temperature inside these worms. And so that we are working on the quantum sensing of diamonds for biological application. And for other than this, and we are also developing a technology for the functionalizing the surface with some chemical techniques, and then feed those nano diamonds to the cells or the C. elegans worms or those things. Those are my research, our group's research activities. Yeah, so that I'm looking for some collaboration opportunities with people who are interested in working on biological applications and also quantum sensing as a protocol for better sensing in biology. Thank you very much for your attention.
Thank you. Can I ask the next speaker to put their slides up, please?
Can you hear me?
We can hear you.
Can you see my screen?
Yes, we're in presenter mode now.
Wonderful, thank you. So my name is from the University of Warwick. I'm nominally in the sensing sort of section, but since we also do some work in quantum computing, I thought I'll sort of briefly mention those as well. So we are a theoretical physics group in the University of Warwick in the Department of Physics, and we work on a bunch of topics. But for this meeting, I'm going to focus on sort of a subset of those and not really talk about our work on sort of fundamental quantum technology for fundamental physics. So as I said, we are a theoretical group, and of course, we seek collaboration with experimentalists and other theorists from various places. So on the computing side, we really work on two problems. So one is one of efficient quantum algorithms, and within that, we focus on solving differential equations, in particular hard nonlinear PDEs. Plasma physics is a sort of an example we work on at the moment, and we have a project, upcoming project with the NQCC, supported by the NQCC on that. The other problem we are interested in is the verification of quantum computing. So as you know, as quantum computers get bigger and bigger, they are getting closer and closer to solving problems that classical computers cannot solve. But as far as I know, all the ways at the present, these outputs of these computers are verified is by solving the problem classically. And this is necessary because quantum computers have errors in them. Of course, solving the problem classically means you don't need the quantum computer anyway. So this is a bit of a foolish strategy that is not going to scale. So we have an efficient strategy of verifying the outputs of quantum computers. And I give one of our recent papers here. Now coming to the sensing part, so we really work on a couple of things. So most relevant for this is probably spectroscopy, quantum light spectroscopy. So here the underlying physics problem is really the interaction of quantum matter with pulses of quantum light. So this is beyond sort of textbook quantum optics light matter interaction. But that enables us to answer sort of basic questions. For instance, if you see on the diagram on the left, does entangled light help in spectroscopy of complex molecules and so on? We also have some work on microscopy or imaging to use sort of quantum techniques to enhance resolution, for instance, in localization microscopy. And at the very end, I want to highlight one recent work, which I'm quite excited about, which is quantum sensors for space or in space for Earth observation and space weather. So we have a couple of projects, one with the UKSA and one with ESA on sort of using optomechanical sensors. So one of the earlier speakers mentioned atom interferometry and Rydberg atoms and magnetometers. We are working with groups in various places on levitated optomechanics for sensing space weather and Earth observation. And we have a proposal to place some of these things on the International Space Station on the part which interestingly happens to be what's called the JEM, the Japanese External Module. So these are the main sort of research highlights from our group. If you're interested, by all means, have a look at our website where you can find my email address. Thank you.
Thank you. Can I ask the next presenter to put their slides up when ready?
Hello, can you hear me okay?
I can hear you. Your slides aren't in presenter mode, just to highlight.
Not in presenter mode. Let me share the other screen then. Is that working now?
Yeah, that's
great. Thanks. So, hello everyone. I'm Gavin Morley from Warwick University. I'm a professor in the physics department, and my research group is experimental, and it's all about nitrogen vacancy centers in diamond. And I'm also the founding director of Warwick Quantum, which brings together 20 academics, 20 research groups, including Animesh. Great to speak after Animesh. And it's also great to talk about NV centers because you've just heard a nice introduction to them. And here's a big picture of a 1 millimeter size diamond with loads of NV centers in it. And that's the sort of thing that we use for our magnetic field sensing. So we have one of these diamonds here. It's at the end of an optic fiber. So then we send in green laser light. We measure the red light that comes back. And we also send in microwaves. And we can use this to sensitively measure the magnetic fields of various different things. Like we were looking at this electric scooter here, which we brought into the lab, which was something that we could detect the magnetic field from. What we're more interested in particular recently, is detecting fusion diagnostics for a tokamak power plant. And so we're working with people like UK AEA, the Atomic Energy Authority on that. We'd be very interested to talk to Japanese fusion people. Also, we've made nanodiamonds with the longest spin coherence times, working with Ollie Williams' group in Cardiff. We've made these 100 nanometer size nanodiamonds with the longest T2, T1, T2 star times, which is very useful for biomedical things, but also our quantum, our fundamental physics work where we're levitating these diamonds. So there's a summary of some of our papers, and do please get in touch if you'd be interested to discuss opportunities together. Thanks very much.
Thank you, Gavin. Can I ask the next speaker to put their slides up? Gavin, you're still sharing your screen, just to let you know.
Yeah.
I'll take this opportunity just to say that we are overrunning. The remaining speakers, if you can try and stick to 2 minutes, and we'll adjust time to allow everyone to talk.
Right, can everyone see my slides?
We can see the slides.
Super. So I'm Jan Mol. I'm a professor of physics at Queen Mary University of London. And at Queen Mary, we have a strong activity in molecular quantum materials and quantum devices. And this covers a broad range of topics. So we work on atomically precise quantum devices, so where we combine organic chemistry with graphene nanoelectronics to place spin centers with close to atomic precision within these graphene-based single electron devices. We also work on quantum thermodynamics, so studying the thermodynamics of few electron quantum systems. This is both for sort of fundamental research of studying concepts of quantum thermodynamics, but it's also to make very sensitive thermal devices such as thermometers and bolometers for the kind of experiments that Adrian Bevan was just highlighting. And then finally, we're looking at topological quantum materials, frustrated spin systems. At the moment, mainly looking at the theory of these materials, but we're slowly starting to develop experiments on this as well. So the skills and expertise that we can bring to a collaboration. So we combine organic chemistry with nanolithography techniques, especially with scanning thermal probe lithography. We do theory on quantum thermodynamics and on frustrated spin systems as well. And then finally, we have experimental techniques, millikelvin quantum transport, and also spin resonance techniques, which my colleague Yunji Liu will be talking about later on as well. And I'll put my details in the chat.
Thank you. Can I ask the next speaker to put the slides up, please?
Can you see the slide?
You can see the slides, yeah.
Okay, yes, thank you very much. My name is Junji Liu. I'm at the Queen Mary University of London. I'm a lecturer in physics and Royal Society University Research Fellow. My research is mostly focused on quantum spin systems, and the particular type of the system I work on is like molecular magnet or like atomic dopants in semiconductors. And I'm interested in those kind of systems because they are very fascinating coherence behavior. And also in some cases, you can tune the system with chemical engineering to engineer the desired property and the potential as a key component for quantum spintronics. So as Yang just mentioned, so in my group, I'm experimentalist, and the technique we used is the electron spin resonance. And we have a standard Bruker ESR bridge in Queen Mary, but I would like to say that many of the results I'm going to show today is actually the measurement was conducted with a custom-built ESR bridge we developed and also the probe head. And this custom-built system actually gives us a lot of more capability, which allows us to conduct experiment that is very difficult or even impossible to be conducted in a standard ESR setup. So let me see. So I'm going to talk about some of the two active research projects in my group. So one of the projects is that we're studying the coherent magneto-electric couplings in quantum spin systems. And we want to see if we can use the electric field rather than magnetic field for spin control and readout, because this would be beneficial since it's possible to confine electric field in a very small spatial space, but it's very difficult to do that same thing for magnetic field at a nanometer scale. So in our studies, we have found a very strong coupling between the spin and the electric field, which is almost comparable with the magnetic Zeeman interactions. And we're also working with our collaborator in chemistry. We found a way to tune those kind of the magneto-electric coupling in quantum spin systems. And we have also demonstrated that by using the combination of electric field and the magnetic field, we could achieve a certain type of the selective spin control, which is impossible for any conventional magnetic resonance technique. And the second topic I want to talk about is actually we're also looking at the spin systems with a spin bigger than 1. So we call them qubit rather than qubit. And those type of the high dimensional system gives a high dimensional Hilbert space, allowing us to do things like for implementing a fault-tolerant logic qubit, which can be used for quantum error correction in a hardware-efficient way. So using a hyperfine coupled electron and nuclear spin systems, we have developed protocols, and we demonstrate in experiment the encoding process of this kind of the logical qubit, and we can measure the spin dynamic of the logical qubit. So here I listed some of our published research result, including some preprint. And if you're interested, we can talk about more in details. And I will be very happy to establish more collaborations both with the UK and within Japan. Thank you very much.
Thank you. Can I ask the next speaker to put their slides up when ready?
Can you hear me and see my slide?
Yes.
Okay, thank you. So I'm Takuya Iwasaki from National Institute for Material Science, Japan. I'm an experimentalist for material science. So we've been investigating two-dimensional materials, in particular graphene and hexagonal boron nitride, HBN, and their stacking structures. So graphene is an atomic layer carbon sheet, and it could be a good candidate for spin qubits due to its spin coherence properties. In addition, a stack of graphene and hexagonal boron nitride, or two monolayer graphene sheet, so with a certain stacking angle, it has a Morley pattern. So this so-called Morley material gives rise to intriguing quantum phenomena related to strong electron collidation. So we aim to explore novel quantum phenomena and device functionalities in these materials. This slide shows the example. So we've been characterizing transport properties in graphene-based quantum dot devices. In this system, single electron tunneling depends strongly on not only the electron spin, but also its the Valley degree of freedom in graphene as a good quantum number. So it is expected to utilize the Valley degree of freedom in graphene as a good quantum number. We can expect to control the spin and Valley coherently and implement novel qubit devices. We've also been studying the spin and Valley, studying the standard Holber and FET devices. So based on the Morley materials, so in which we investigate the Valley Hall effect and the quantum anomalous Hall effect and so on. So for future low power consumption devices, if you have an interest in our research and have any questions, so please contact me. Thank you.
Thank you very much. Can I ask the next speaker to put their slides up, please?
Can you hear me? See the slides? Everything okay? Yeah.
Yes.
Thank you. Thank you. Thank you all for the invitation. So I'm Ismail Diaz-Perez. My name is, everyone calls me Isma. So I'm coming from the King's College London in the chemistry department. We are part of this King's Quantum that Mohammed, my colleague, just presented before, and also we are part of this Center for Physical Science of Life, where we study physical properties in different biological materials. So our group is the biomolecular electronics group. We're interested on quantum effects in biomolecules in general, so especially in charge transport and spin-related properties. So we started like similar to what Jan's previous speaker was talking about. So we started like studying molecular effects in nanoscale contacts. So we can just trap a single molecule between two electrons and then study the chemistry. And lately, our group has been more interested in this higher level of complexity with biomolecules. Another way, the way we measure this is very unique. So in more than 10 years, 15 years, we started to develop this methodology where we can create a nanoscale contact between two electrodes. This is all in physiological conditions, in aqueous solutions, in the biological medium, and then we can trap individual proteins on biomolecules and then study the transport properties with a very high precision. And then those trapping events are very short because, we work in ambient conditions, physiological conditions, but, they're enough for us to extract all sorts of electrical information from the single protein junction, like current voltage, transistor curves, force, electromechanical properties, or spin injection. And then we can do statistics and then gather all this information about the quantum transport in these particular biomolecular systems. Now, the interest in biology, in electron transport biology is very, very extensive. So essentially, there are many functions in life that depends on the move of charge efficient across the systems. And then here are some examples: aerospace photosynthesis, for redox enzymatic catalysis. And we know that the way these biomolecules move electrons are very efficient. So it has long range, high efficient electron transport. And this is something that we coin as the effect of supramolecular electrons. So it's simply this special structure and supramolecular interactions in these biomolecules that are really enabling this high efficiency transport. So now with these systems, I'll show you just very quickly the type of things we're looking at. So we have a project on bioengineering single protein junctions where we chemically modify the surface of the protein and then connect in different orientations so we can map out the landscape of electron transport in these biomolecules. This is also important for something that in biology is very, very interesting, which is post-translational modifications. So you modify the surface of the protein and then how this change the electrical properties of the protein that enables these proteins to signal itself for something for death or in cancer mechanisms. Another very interesting project we do is study these electrical bacteria proteins that are part of the electrical bacteria. Electrical bacteria has these systems that can translocate electrons at very long distances, and the proteins that are conforming these structures are multi-heme proteins, and we're studying how the electron conductivity at this long range is possible, is enabled in the systems. And then one thing that we do also is a spin in biology. So we're interested in injecting a spin into these structures and see how the spin scatters different. And this is a very interesting problem that we started a few years ago. We saw that this kind of helical structures in biology can really spin filter the current. And this is interesting for example, avian navigation, how birds oriented in magnetic field, or for example for redox enzymatic catalysis, which is the last project I want to show you. Well, we look at redox enzymatic catalysis at the single enzyme level. So we can electrically transduce individual events from these systems and study the heterogeneity of this very important biological function in life. So just the last one. So we are interested in collaborating on all those systems. So we are very keen on looking at quantum effects in biology and also in sensing, biosensing, and transporting, for example, enzymatic catalysis of other biologically interesting phenomena. Thank you so much. I put my email, and thank you so much.
Thank you. Can I ask the next presenter to get ready to present their slides?
Thank you. Yeah, thank you very much for giving me this opportunity and the only talk in the other quantum technologies category. My name is Thomas Busch. I'm a professor at the Okinawa Institute of Science and Technology in Okinawa in Japan. And what we're interested in is quantum energy, in particular quantum engines, and everything related to how energy flows and how energy is processed in the quantum regime. We're in particular interested in the physics of quantum many-body systems for quantum technology applications of these quantum many-body systems, beyond single particles or two-particle systems. And with this particular, how quantum engines can be run efficiently, how quantum batteries can be run efficiently, or how any kind of dynamical control can be exerted in these systems. So what we are looking for is theory groups with a similar interest, theory groups in particular with a strong quantum thermodynamics expertise, not necessarily focused on the quantum many-body aspect that we are focused on, but also experimental groups. And I'm going to say this in a minute, we're very interested in the ultra-cold atomic area. Yeah, the ultra-cold atomic atoms or the ultra-cold atoms are our favorite system. And I would like to very briefly walk through this example of a quantum engine of the kind of work that we think we're interested in. If you think of an engine, you have usually some kind of container and a medium that works. And in our system, this is something like down here, a gas in a trap. You do work on the system, you compress it, then you heat the system up, the atoms kind of take on a different distribution. You do work on the system, you open up your box again, and then you get heat out of the system again. You can run a classical Otto cycle in these quantum mechanical ultra-cold atom systems. And what this in particular means, what you see on the right-hand side here, Adding temperature to a system means a change in statistics, which is not very surprising because everybody knows the formula for quantum statistics. There's a T for temperature in there, so if you change the T, you change the distribution. This is all classical. If you want to do this quantum mechanically, you need to change something quantum mechanical, and what you can change quantum mechanically is the quantum many-body aspect, namely the statistic nature of the particles. The distribution function is a plus minus in the denominator, and if you change this, you also change the distribution, and you should be able to build an engine. So by changing the quantum part, by turning the plus into a minus, you can create an engine. And this is something we recently looked at together with an experimental group in Germany, where we start out with the gas of bosons, we do work at it by compressing it. Then we change the statistics from bosonic to fermionic. We do work on it again by expanding it, and then we change the fermions back to bosons. And by this, you can actually construct a fully quantum mechanical energy cycle that gives you out work. It's a very weird cycle because it's fully reversible. You usually don't think of engine as reversible. There's no bath, it's not coupled to a heat bath or something, and it is actually running at constant entropy. This is the kind of systems that are only possible in the quantum regime, and would be very interested in finding partners to help us explore this. In particular, we're interested in the optimization of these engines, in the outcoupling of the work, i.e. making them useful. This is like proof of concept experiments and very, very early ideas. Maybe finding something in the classical quantum hybrid space, which works even better. And in particular, with the audience here, we're looking at ultra-cold atoms, which are our favorite system, but there are the materials, for example, superconductors, where you can turn fermions into bosons and vice versa. We would be very much interested in. My email address is here. If you have any interest, please feel free to get in touch just anytime. Thank you very much.
Thank you. I'm just going to say, because we're a little over schedule, that I'm going to propose that we all take a break now until 11:40 and then come
I thought we had one more presentation, sorry. Tom?
no, that's the
Sorry,
presentation.
you're right.
So if we all take a break till 11:40 and come back, and then we'll go into breakout rooms fairly promptly. Thank you.